यायचं होतं पण अवघड आहे.
Hey everyone, welcome to lecture number 15. I hope you're having a nice week. I see some students streaming in, so that's great. Before we dive in, we've got a couple announcements. I've already turned off my video because we already had call quality issues. So just audio and screen share for today. Hopefully the internet gods smile on us. I might do some more of that fun overhead camera view, maybe in a future lecture, but today it'll just be audio and screen share. But it should be a good lecture. We get to talk about neural networks, and we are going to dive into autonomous driving, which will be pretty cool. Before all that, though, I want to go ahead and hand it to Aravind real quick. So Aravind, if you could just share a little bit about, we just want to make sure you guys have a good understanding of what's expected from you as far as the group meetings. Yeah, Aravind, I will hand it over to you for a quick announcement.
Thank you, Professor. You're able to see my screen, right?
Yep, I can see it.
So every week we have meetings with one or the other groups. So for this week, so here are the dates for every week which we have meetings. So currently this is October 27, 29, 30. We have slots on Tuesdays, Thursdays, and Fridays. On Tuesdays and Thursdays, we have after the class 2 slots, 4 p.m. and 4:15 p.m. And Friday we have 4 slots, 4, 4:15, 4:30, 4:45. So for every week, groups should actually check this spreadsheet on which week they have meetings, and they have to book their slots on using the links screen over here.
Mm-hmm.
So this is the schedule. This is a schedule link, and this is the calendar link where you can book your slots. So for this week, we have meetings with groups 1, 2, 3 with the TA, and 7, 8, 9 with the professor and the TA. And this is a repetitive process. For every week, you would be having meetings either with the TA or with the professor and the TA. So kindly just look at the schedule and make sure you book the slots in that particular week. Yeah, that's it, Professor.
Great, thank you so much, Aravind. And yeah, this is a requirement, so it's not optional. So make sure you get your meetings booked. These help you keep your groups on track and help keep things moving. And it's kind of a nice way to get a little bit more face time, you know, because that's one thing we miss from in person for sure is having that kind of face-to-face dialogue. So on little calls with 4 or 5 team members, it's a lot nicer, you know. And I think the students who are here who have had a meeting already, I hope you enjoyed it. I think that the ones we've had so far have been productive. So yeah, make sure you get those scheduled. You know, those are there to keep your projects on track. Don't forget your project is the biggest part of your grade, right? So we want to make sure you all have successful projects in less than 2 months until they're all done. So we're approaching these deadlines quickly. Okay, great. Rohan, any updates or announcements from you?
No, Professor.
Okay, wonderful. All right, great.
I just wanted to add one more thing.
Yeah.
So all the lecture videos are up on Canvas. Just to let you know, because for the programming challenge, if someone might miss the lecture number 13, they can just go to Canvas and look at the lecture video.
Wonderful, thank you, Aravind. Yep, we have all the videos up to date now. We got a little bit behind. It's actually 100% my fault, so I'm the reason that there's a delay. So I'll try to stay more on top of that. Rohan and Aravind give me the videos. I'm the last one who uploads them. So we should be, today's lecture should be up soon. But yeah, especially the neural network lecture so far will be relevant for your programming challenge. So do look at those if you need to. You've got the whole lecture recorded there. And those are up on YouTube and linked through Canvas. Okay, so let me go ahead and start a screen share. So let's see here. So application window, okay, here. So the next thing I want to remind you of is the next big due date here is definitely your autonomous driving neural network challenge. And this is the hardest challenge of the year, so I encourage you to start soon. This is due in less than a week. And we have some nice instructions for you here, and we're going to be talking today and on Thursday about kind of the approach, that you would take. But again, the material that we're going to cover in class this week is not going to tell you how to do the challenge at all. It's really up to you to go read the challenge, have a look at it, and figure out how you're going to solve it. I'll give you a couple of tips today, but again, these challenges are all open-ended, so don't wait for a lecture to tell you what you need to know, because that lecture will never come. We're not going to tell you exactly how to do it. So we will give you instructions and direction and ideas, but but it is open-ended, just like the rest of them. And I think in sample student, do we give you a neural network to play? Oh yeah, okay. So we give you some nice sample code. Yep, definitely. So we give you a pretty good starting point, and the starting point it's very similar to the code that we're covering in lecture. So it's there, and do get started. I would encourage you to certainly start. If you haven't started yet, please start today or tomorrow. Because yeah, less than a week, and this is the hardest one of the year. And I say this every time, you're probably sick of me saying it, but for whatever reason, every year that I've taught this course, we've had someone unfortunately cheat on this assignment, and in some cases more than one person. So make sure that your code is your own. So what usually happens is if you put this off too late, Sunday night rolls around, Monday night rolls around, and it's last minute, and you borrow some code from someone, please don't do that. We have to prosecute you, and it's not fun, and you get reported to the Academic Affairs Office. So make sure that your code is your own. You can use my code, that is completely allowed, but other than that, the code has to be your own. You are free to discuss ideas with your classmates. Just be careful. If you write some pseudocode on a whiteboard or you share some pseudocode, make sure that when you go to write your final code, it doesn't exactly, make sure it's different. And just changing variable names is not enough. Our code will catch that. We need you to be writing your algorithm in your own style, and it needs to be your own code. Okay, so that's the autonomous driving challenge. We'll dig into this some more today, into some of the background and stuff, but you have everything you need to get started. Great. Yeah, it's a good question, Monica. So there are no right solutions to the programming challenges. That's a good question, Monica. Absolutely. So let me make sure I understand Hernan's question. So Monica says we will never get the right solutions for all the programming challenges. I thought we'd get to the end of the challenge. No, so yeah, we don't give out solutions at the end because yeah, there is no one solution, right? If you achieve a good score on the measurement criteria on a leaderboard, then that is a good solution. So Habib, there are not 2 challenges due next week. Let's go ahead and look at the schedule. So here's your schedule. And let's see, so we made it to here. So we are going to finish up neural networks, and we are going to hop into autonomous driving today. And so your programming challenge and quiz are due Monday, November 2nd at midnight. So no, just one challenge. Okay. All right. Cool. Okay. So Hernan's asking about code from the OpenCV documentation. If it's a very common code, then we probably aren't going to worry about it too much. But if you're copying like 3 or 4 lines of code from OpenCV, then I wouldn't recommend doing that. If it's a single line from OpenCV documentation, that's fine. But if it's 3 or 4 lines, something like that, I'd recommend making a change. Okay. And yeah, Monica, it's a great point, Monica. We can talk about it. Let me hop into lecture here, Monica, but yeah, it's a great point, right? So Monica's basically asking, how do we know if we did well in the programming challenge, right? Yeah, so traditionally we don't, review them in a lot of detail. And again, that's because we want to keep the challenges for future years and stuff. But in the past, students will kind of discuss the ideas that they use and things like that. And we will, in class before, we have discussed general ideas about solving the challenge. So that might be appropriate this year. I think that's something we've had students ask for in the past. Can you tell us, generally the solutions you use to solve these programming challenges? And once or twice, we've actually had some of the top submitters explain their solution in class. So maybe we could do something like that. If that's something that's popular, then maybe make a Piazza question. You guys can discuss it there. We're open to doing that. We've done it in the past. Like I said, we've had students, some of the top submitters, share their solution. So that's definitely an option. But Monica, just part of the answer is there is no one solution. I mean, I have solved the challenges myself, but I don't consider my solution to be the one right solution, and I could share parts of it and things like that. And you could also ask me in office hours. So hopefully we can find a way to give you what you're looking for, Monica. Okay, cool. So let's get into our lecture today. And I really want to finish up this neural network section. And in the last class, well, actually, sorry, before I hop in, there's one more thing I have. What did you guys think about David Deco? So yeah, throw it in the chat window. Thoughts, things you liked, things you didn't like, things that you thought were interesting. What did you think of our guest lecture last Thursday? Yeah, the optics are interesting, right? So in machine vision, they spend a lot of time thinking about cameras, right? We'll talk about cameras in our very last module, but we don't spend a ton of time on cameras, right? We spend more time on algorithms, right? The hardware was cool. I agree. They do some really cool hardware, right? That golf ball thing was crazy. Any other thoughts? What did you guys think of the talk? Okay. I thought it was really interesting. David Decko's a super nice guy. If you're interested in machine vision or anything like that, I encourage you to reach out to him. He pretty much offered. You could shoot him an email, and he's very open and supportive of students. Cool. Yeah, the hardware is really interesting, right, Monica? Yep, definitely. One other thing I would like to point out, he went off. Oh, so Sai, you heard back from him. That's great, Sai. That's awesome. Cool. That's great. Good. Yeah, he's a great person to know. Really well connected, super smart. One point I just wanted to point out really fast. So David Decko does not really do machine learning. And most of machine vision today does not use machine learning. And it's a very interesting area, right? And he solved the finger counting challenge just brilliantly with using no machine learning at all, right? Using fully analytical techniques. And we're going to talk about analytical techniques in some more detail, but basically he just has been in the industry so long that, I'd love to see his solution to brick ball cylinder. I think he would do really well. I don't think he would beat deep learning at that task, but for some tasks, what he's going to do is going to be better, which is pretty cool. There's this really interesting development right now where deep learning is becoming more and more of a popular technique, but it's very interesting to see what people can do with what he calls a discrete vision, right? So there's nothing wrong with either approach, and sometimes people say, oh, there's only one way to do it. But there's nothing wrong with either approach, and it really makes me curious to see what he could do on some harder problems. Like I would love to see David try brick ball cylinder hard, like the brick ball cylinder hard images. I don't think he would do nearly as well as deep learning, but that's not really the kind of problems that he solves. You could tell that in his industry, like you make the background simple, like you do that with hardware, for example, right? So I don't know. I think it's really, really interesting to see other approaches. And he was using software called Halcon, it's a proprietary software, but it's pretty cool. It has similar functionality to OpenCV, but it's pretty cool stuff. So Sai, it is not compulsory. So Sai asked, is it compulsory to use deep learning for the course project? So no, definitely not. We've got a couple of groups not using deep learning. You do not have to. Deep learning is an area where you can generally do kind of more cutting edge stuff, but by all means, there are plenty of problems where deep learning is not the right answer. So no, you are not required. And that's why we have these individual meetings with the groups to make sure you have a good approach. And deep learning is not always the answer. Really, you want to look at the problem and look at the technology and decide what's the right fit. And I hope that you guys at the end of this course have a better understanding of that yourself to know when deep learning is the right thing to do. Because if you just read like the press or the kind of the popular blogs and stuff, they make it sound like deep learning is the only way to solve these problems, but it's not. It's definitely not. Okay, so I could chat about that for forever, but let's go ahead and get in today's lecture. So we want to finish up this Neural Networks Demystified series, and we did a bunch of math last time. Remember that the idea here was we're going to try to train a little neural network to predict our score on a test based on how many hours we slept and how many hours we studied the night before. And we have this little data we made. Excuse me, maybe this. No, like this. I'm trying to insert a new cell, but it's going terribly. All right, let's go cell, insert cell below. There we go. I was trying to use a keyboard shortcut. Anyway, we have some data. It looks like I added one more data point for this notebook. We'll see why shortly. And I'm not going to go all the way through this notebook. I just want to hit the really big important points. Because we're a little short on time today, I'm really going to rely on you guys to spend a little more time watching the videos. So you do have videos that cover everything in this topic, and I want you to spend a little bit of time in the notebook yourself. This notebook, Neural Networks Demystified Part 2, which is in the repo, this is probably your most helpful guide when you get to the programming challenge. So this is the first place to look. Okay, so here's our neural network, and we've already seen, I think you've already seen all of this. So all of this we showed last time, and we set up these hyperparameters, we initialized our weights. This is our forward propagation where we take some input x and we map it or do the math to make a prediction, which we called y hat. And now there's some new stuff. There's some new stuff that you haven't seen yet, I think. And really, the new stuff is mostly here. So there's a few more things in our class down here, but these are kind of just helper functions. Really, like the new stuff is here. So I want to talk through these functions real quick. So first of all, what is sigmoid, right? Why is this here? What is this sigmoid thing doing? What is that called? Yeah, it's our activation, right? Does anyone remember why we need an activation function? Like why just not leave it out, right? Why do you need an activation function in a neural network? Yeah, great, Abhijit. It allows you to learn nonlinear patterns. Perfect. Okay, cool. So what about this? What is this? What is this sigmoid prime thing I've introduced? Where did that come from? It's the derivative. Thank you, Abhijit. So sigmoid prime, that is the derivative of the sigmoid function. And why do we need to take a derivative? How did calculus sneak in here? Why are we taking a derivative? Yeah, so Abhijit said gradient update. Hernan said to find the slope, right? Yeah, exactly. And this is all part of training, right? So to train our neural network. So if we just wanted our neural network to make predictions, all you actually need is this. Like this makes predictions, like you're done, right? But if you want it to make good predictions, then you got to update these weights. And the way we decided to do that is with gradient descent, just like Sai said. And part of that is to find the rate of change, the slope, the derivative, the gradient of our cost function relative to our weights to allow us to optimize our weights. That's the big idea here. Okay, so that's sigmoid prime. What is this? What is this cost function thing? Why is this here? What does this do? Yeah, so Abhijit says overall performance of the model. Subham says error. Yep, okay, fair enough. Yeah, definitely. And there's a special name for this kind of cost function. What is this called? This has a special name in mathematics. Yeah, MSE. What does MSE stand for, Abhijit? Oh yeah, there it is. So I got it. Yep. So mean square error. Yep, perfect. So we're using the mean square error. When we get to deep learning, we're going to use a different loss function called cross entropy. For now, we're going to use this mean square error thing. Okay, cool. Now, here's where it gets really interesting, I think. Someone please tell me about this function. How would you explain this function to someone who doesn't know about neural networks, right? Why is this function here? What does it do? What is this cost function prime thing? Okay, so it's related to backpropagation. Let's be more specific though. So sure, it's related to backpropagation, but what is it really doing? Tell me in more words. So Nick says it shows how the error changes as we change the weights. So that's really great, Nick. I would change the order of what you said. I would say it shows how the weights change. No, actually, no, take it. Your order is perfect. Sorry, I thought your order was backwards, but no. Yeah, so Nick's description is really great. It connects it's how the error changes as the weights change. Yeah, perfect. So Pooja, you said minimize error, which is close, but this actually will not minimize error alone. This only tells you how the weights or how the error changes with respect to the weights. It's part of minimizing the error. And Hernan, so yeah, you're really close too, but remember that all this does, and we're about to get into this in more detail, it doesn't like update the weights for you, it just suggests how you should do it by telling you how the error changes as your weights change. Yeah, so Jagadish, I like your answer as well. Yeah, cool. Okay, so great. So that's cost function prime. Now, real quick, look at all these NP dots, these matrix products, right? So this one might look familiar. Like, where did this come from? Did I just make this up? Like, where did this line come from? Can anyone tell me? Sure, multiplication rule. I think the thing I want to point out, so remember that, a week ago today, I got out a bunch of paper and we did a bunch of math, right? We did a bunch of calculus, okay? So the answer to like number 11 or number, I forgot which number it is, but this is like the answer to one of my questions. So basically like this came from calculus. So we make some assumptions about how our network works, like what forward propagation is. And then we do calculus to figure out, you know, this just comes from doing calculus. It's analytical, it came from doing calculus on paper. That's where we got it from. We didn't look it up in a book, we did the calculus. Cool, okay, great. So that's cost function prime. I'm gonna kind of skip this stuff for now. This is just kind of helpful stuff. We're gonna be using an optimizer in a minute from a library called SciPy. And that optimizer prefers that you have all your parameters in one vector, and it prefers to give you new parameters in a vector. So these are just wrapper functions that make life a little bit easier. So don't sweat those too much. The things I really want you to understand are, of course, the kind of the forward propagation things, the setup, and then I want you to understand these three functions as well. Okay, so that's our neural network. Now here, this is really like, if you only walk away from this module with one piece of intuition, and yes, that means it will be on the quiz. If you walk away with one piece of intuition, I really, really, really want it to be this. Like, I really want this to sink in. This is the heart of deep learning and neural networks. This is it. So if this sinks in, I'm super happy. If it doesn't sink in right away, that's fine. Come back and look at it. This is like the most important concept. Okay. So as usual, I have set this up as a multiple choice question, and Rohan and Arvind, if you guys could get a poll ready, don't trigger it quite yet, but if you could get a poll ready, just A, B, C, D, that would be perfect. Thank you. So yeah, let's go through our math. So I'm asking you a question. I'm saying which cost will generally be larger. So let's go through the code here. So what I'm doing, I'm instantiating a neural network, right? So I'm using the exact neural network that we just coded up, right? And then I'm computing a cost. So I'm saying, okay, remember X and Y, those are like that's our data, right? I'm saying, here's some data. Please tell me the cost, the loss, tell me how bad our predictions are for this X and for this Y, right? And then I'm computing the gradients. I'm saying, okay, give me djDW1 and djDW2, which are the gradients with respect to our weights. And just remind me really fast, guys, does anyone remember, this is djDW1, djDW2, how many weights are there total? How many total weights are in our little baby neural network? There's 9, thank you, yep, good job. And remember that this is the first layer weights. How many weights were there in the first layer? Does anyone remember how many weights are in the first layer? 6, perfect, and there's 3 in the second layer. Great, okay, good. A lot of folks remembered that, good. So these matrices are the same dimension as our weights. I believe this is a 2x3. This is, I think, a 1x3 or a 3x1. I can't remember, but there's 6 numbers in here and there's 3 numbers in here. And this gives us the gradient, the rate of change of our cost with respect to our weights. So that comes out here. We compute that. Now, we have not discussed this idea of a learning rate. And it's going to be a big deal, but I wouldn't sweat it right now too much. We'll explain it in a second, but just accept for a minute that there's this constant that we're going to call the learning rate. It's a very important variable, so when you're doing your programming challenge, I'd recommend playing with the learning rate. But here's what I really want to point out. So look at what I'm doing here. So I'm taking the current weights, the current weight matrix, right? Well, I should say here, I'm taking the current weight matrix, and I'm adding to it the learning rate times the gradient, right? Okay, so learning rate is just a scalar, right? It's just 0.1. djDW1 is a 2x3 matrix, and W1 is a 2x3 matrix as well, right? So it's kind of like a point-wise addition, right? So I'm taking this matrix, I'm scaling it by 0.1, and I'm adding it to the initial weights. So I'm kind of like updating the weights, right? So I'm replacing the weights with the original weights plus some change, right? Okay. Here I'm doing the same exact thing, just with the W2 gradient, W2 weights. And then what am I doing? So now my neural network has a new set of weights, right? And I'm measuring the loss again. So I measured the loss or the cost, I measured it once, and now I measured it again, right? And remember that the better our neural network is doing, the lower our cost function. So good performing weights should have lower costs. Okay, so that's all well and good. Now we're gonna run this code in a second, and it's your opportunity to make a prediction. So I would like you to predict what the answer is gonna be. So do you think that cost 1 is greater than cost 2? Do you think cost 2 is greater than cost 1? Do you think the cost will be equal, or have I not told you enough information? So yeah, let's go ahead and throw up that poll, guys. Thank you so much. And let's take 30 seconds to think about this, and we will talk about the answer. Okay, thank you. All right, so the most common answer is A, which is cost 1 is bigger than cost 2. The second most common answer, kind of a tie, three-way tie for B, C, and D. So A was the most popular. Okay. So those of you who said A, let's see, are you right or wrong? I have to think about it for a second. I think you're wrong. I think you're wrong. So I don't think A is the right answer, but let's talk about it. Let's kind of get into it. So I'd really like to get into it in some code is what I'd really like to do. I'd like to actually try it. And I kind of want to break this down because I want to make this really, really clear. And I might go back to a drawing. This is where I normally draw on the board. Maybe I should have set up my overhead camera recently. Why can I not? There we go. That's what I've been trying to do. So I'm going to just take exactly the beginning code, right? So, and let me put a few spaces. Okay, cool. All right, so now you can see this really nicely, hopefully. I might zoom in just a little bit more. Yeah, that should be showing up pretty well. Let me know if you have any trouble reading. Okay, so we've got X, we've got Y. I computed these gradients, DJ, dw1. So I got this gradient out. Here's the gradient. This is the rate of change of our cost with respect to our weights, right? Here's DJ dw2. There it is. And now the next thing we're going to do here, right, is we're going to increment our weights, right? So we're going to change them. We're going to update them by multiplying the learning rate times the gradient. Okay. Here's what I really want to get at. I think I'm actually going to go back to lecture number 1 to show you this figure again. I really want to show you this figure. So let's think about this problem in 2-dimensional space, or maybe even 1-dimensional space for a second. Here's what I really want to show you. I want to look at this. Yes, wonderful. Okay. So let's look at this picture for a second. So what we're doing right now really lines up very well with this picture, right? So we have some initial weights, right? And we measure our cost, and then we measure our gradient, right? Okay. So remember how derivatives work, right? So, and man, I should have, now I really want to draw this. I didn't think I would want to draw this, but now I really do. So I'll open up my drawing app in the background, but in the meantime, let's kind of hop into this. So let me ask you this. This picture, right? And I'm kind of telling you, but let me ask it. In this picture, right, if I take the gradient of this function, is my gradient going to be positive or negative at this value at 1.1? Will this return a positive or negative gradient? Is the slope positive or negative? It's negative, yep, thank you. Yep, everyone says negative, cool, okay, great, good. So for this weight, right, dJdW whatever is going to be negative, okay, and that's because it's going downhill, right? If this was going the other way, if it was going like this, right, then I would get a positive dJdW, right? Okay, so in this image, I get a negative dJdW, right? And my next question to you is this. To make our cost lower, if we're sloping downhill like this, should we increase or decrease W? What should we do? We should increase, right? Yeah, so Ravina has it, right? Yes, absolutely. We should increase. Okay. So if we're going to be adding dJdW to W, right? Or subtracting, I don't know, we haven't decided yet. But if you, let me back up. Here's what I really want to show you. So let me go back to the question I asked you. So look here carefully, right? So I took my weights and I added dJdW, right? I added the slope. I added the gradient, okay? So what will that do? Look at this picture. this is negative, right? So if I add a negative number, which way do I actually move, right? Does W get bigger or smaller if I add the gradient to W? It gets smaller, yep, great, awesome, cool. So it gets smaller, excellent. It gets smaller because I'm adding a negative, right? So what I really want to do to make my cost smaller is I actually want to subtract, because if I add a negative here, right, if I add a negative, this will get bigger, right? So we'll actually get a bigger cost, which is going to get us back to the answer to our question in a second. And if you switch this and your slope actually goes uphill, if you have a positive dJW, you'll observe the same thing basically. So if you want to make your cost smaller, you should subtract, you should go downhill, right? And if you add your gradient and you're going uphill, your cost will again get bigger. So adding actually does like the exact opposite of what you want. So I've kind of asked you a little bit of a trick question here, but what I'm showing you is that, hey, if you add the gradient to the original weight value, you actually end up going uphill. You end up doing what's called gradient ascent instead of descent. And the right answer ends up being actually B, because your cost actually gets worse. You go uphill, you go the wrong way, right? And let me show you the code here. Hopefully that makes sense. That's a really, really important theory. And yeah, so Abhijit asks a really great question. He says, would it not depend on the learning rate? So yeah, I really want to address your question, Abhijit. Let me just show you the result here real quick, and then I'm going to talk about Abhijit's question because it's super good. Okay. So here I've just gone all the way to the end basically, and this is cost 1 and this is cost 2. And you'll see that cost 2 is higher, 0.94 versus 0.094 versus 0.0904. So hopefully that shows you with some data. But yeah, so Abhijit asks a really good question. So it depends on monotonicity, but let's get into the general idea here. So what really happens, Abhijit, is that the sign tells you kind of which way to go, if positive or negative. The learning rate controls how far you go. Now, dJDW, of course, it gives you more than a sign, right? If we look at dJDW, right, it is, you know, you have signs, but you also have, you know, magnitudes. And the bigger the number is here, the idea is the bigger the step you'll take, right? It'll make you move, you'll change your weights more, which should make sense because if this was very steep, you would want to change your weights more, right? That would encourage you to say, oh, I want to take a big step, right? But that's only part of the solution here, because we're multiplying these gradients, the slopes, times the learning rate, right? So what that really affects, Abhijit, right? This affects how far you go. Now, if this function all of a sudden like curves back upward, right? Which we'll get into that soon if we have time. It happens. So if this function curves back upward like this, then you could go too far, and you could go back uphill. Exactly, right? So you do have to tune that learning rate, Abhijit, but kind of the assumption that we make in neural networks is that if you make your learning rate small enough, then when you take this step, you'll still kind of be on this curve. But it's not always true, right? Just like you said. So you're kind of assuming that your learning rate is small enough that you don't hop into the next uphill region and that you've moved downhill, you know, in kind of the little neighborhood that you're thinking about. Hopefully that answers your question. It's a really, really good question because it does depend on the learning rate. Yeah, so if this was on a quiz and you really wanted to argue the answer was D, I would say maybe, like maybe I would let you have credit if you said D. And it's true, you can't know for sure, right? But I did say generally up here in the question. I didn't say always, I said generally. So I could probably say that generally the answer is going to be B, right? If you have a smooth function. But I see your point, Abhijit. You could argue D, but generally the answer will be B, that you will get a bigger cost in this case because you'll go uphill. So yeah, Hernan says, can a large learning rate get you to another minima? Yeah, so I think what Hernan is kind of thinking about is, okay, maybe sometimes you do want to actually jump over, right? Maybe it could jump you to this next minima down here, right? And there's an idea in neural networks called momentum. And I know that as part of their solution, a number of students in the last years have used momentum to help them do better on this programming challenge. And the idea of momentum is that you're going to add a term to your gradient descent, basically. The thing to look up is it's called the Adam optimizer. Adam optimizer. It's really easy to code up the Adam optimizer. And what it does is this takes gradient descent and it adds what's called momentum. And momentum is just like what it sounds like from physics, basically. So this atom paper looks really complicated, but it's actually really simple. It's just a very simple improvement on gradient descent, basically, where instead of just updating your weights like this, you have an extra term that basically carries like some memory with it. And so if you're kind of like rolling down a big hill, like here, that momentum will keep you going and hopefully get you over those little humps. So that is an idea in optimization, and it's an idea that we might use. You may use on your challenge if you'd like to, and we will definitely use it in our deep learning module. But in deep learning, it'll be built into PyTorch, so you won't have to really think about it too much. But it will be there. It will be there, and it's an important concept. Okay, so I hope that makes sense to everyone. Again, this is just an absolutely critical concept. I really want you to feel good at this. You know, please ask the TAs or myself if you're confused. Watch the videos, run your own tests. This is the heart of neural networks. Without this, neural networks don't work. So this is how they learn. This really is how what people call AI today. This is how it learns. Okay, so I want to ask you another question. So here it is. It might look familiar. I'll tell you what, as a test of how well this is all making sense or not making sense, let's go ahead and throw up the poll, guys, if you don't mind. Let's just go ahead and get into this one. So I'll give you 45 seconds or a minute. Maybe let's do a whole minute. So please take a minute, look at this question, see what you think. It's very similar to the last question. And yeah, I'll stop talking for 1 minute and let's go ahead and poll on this one. So have a look at this question, please. Okay, I think we've had about a minute. Did that poll pop up for everyone? I haven't seen it on my side yet. It hasn't popped up. Okay, gotcha, cool. Arvind and Rohan, any issue? I know you guys have slow internet today. Are you able to trigger that poll? Okay, awesome. Thank you, guys. All right, so you should have your poll now. Please put in your answers. We'll close it in 15 or 20 seconds. All right, cool. Okay, so I see 80% on A, so that's great, cool. And then we've got a kind of a tie between B and D, sure. Okay, cool. All right, so the answer is A. The answer is A. In this case, cost 1 is bigger than cost 2. And what was different between this question and the last question? What was the one little thing that I changed that made all the difference? Yeah, minus sign, right? Yeah, cool. So we're subtracting now, right? So we're doing, this is actually gradient descent, not ascent. And we're taking the weights and we're subtracting the gradient, which in a picture like this means we actually get to move downhill. So the cost should generally be smaller, or I should say cost 1 will be bigger than cost 2 because our cost is decreasing. And that really is how this stuff works. So here's the math again. And this really is the heart of gradient descent, like I said. Now we're going to train our neural network now, and we do this in the video as well, but I'll walk through it just briefly here. I'm going to use, like I said, a package called SciPy Optimize that I'm about to import. You do not have to use this package on your challenge, but you can. You certainly can if you want to. If you have any issues with your challenge, or if you're trying to be competitive, then I encourage you, like I said, to look at the Atom Optimizer. So here's the paper. This is just a little tweak on gradient descent. If you Google around, you'll find some implementations and stuff. So I know students have used this method in the past to perform better on this challenge. And you can also actually just use plain gradient descent as well. So plain gradient descent basically would be you just take this code and you put it in a loop. So you basically update your weights, you compute your cost, compute your gradients, update your weights, and then you just loop over and over again. That's kind of just like plain gradient descent. You just keep updating your weights iteratively. We're going to use, like I said, this optimize package. Again, you don't have to. One of the reasons I'm using this here actually is that this is from my neural network series back in 2014. And this was kind of, back in the day, this was kind of how you did things. You used these kind of complicated packages. This uses what's called the Broyden-Shano Goldfarb something optimizer, and this BFGS optimizer. And it works well, but people have learned since then that you can actually use simpler optimizers. So I would encourage you to start with my code, try that, see how it works for you on the challenge, but there are other methods as well. And in some cases, simpler methods. So all I'm doing here is I've introduced a training method basically that is going to run this minimize method for 200 steps. Basically, it runs a loop. So let me go ahead and get that going here. And I want to show you this plot. So this plot, oh wow, it's got nothing. Wow, cool. All right. I think I didn't run this cell. Let's try this again. All right, cool. There it is. Great. So I ran this optimization, and this is a plot of our cost function as we train our network. So you can see that it's going down, which is good. A lot of times when you train these networks, you'll have, if you have a bug, the cost may go up as you train. But you can see the cost coming down. These are iterations, so these are gradient descent steps. So we've trained our network using that method that I just mentioned, and I kind of glossed over it, but please do review this. We're using this SciPy Optimize method. And these are actually, yeah, let me pause for a second. So I do want to get into autonomous driving, but I want to make sure I spend enough time on this to make it really clear what's going on. So yeah, let me just ask you guys this question. So now that we've trained our weights, right? We trained our model. What should be the value of the gradients? What would you expect, right? So if we've really, yeah, so Abhijit says close to 0. And why should our gradients be close to 0? Anybody? Yeah, we should be at a minima, right? You should be at the bottom of a 9-dimensional bowl, right? Yep, totally, cool. Let's try it so we can do it here. So here are our weights, and if you have a look, they're mostly pretty small, right? So these are very small numbers, much smaller than what we started with. So that's a good sign, right? It means that we hopefully have found a minimum. We don't know if it's a global minima, but we have found a minimum. Okay. So all I wanted to show you now, I just wanted to point out one last thing about neural networks, and then I think we'll hop to autonomous driving. So this is all in the video, so I encourage you to watch the video. You'll see it there, but I just want to point one little thing out, which is that up until now, we have ignored what I said earlier in the year was like the most important thing in machine learning. So back in the Learning to See module, right, I said, hey, make sure that you don't overfit. And in that module, we were talking about decision trees and other kinds of machine learning algorithms, but now we're talking about neural networks. And overfitting is definitely still a thing, right? And we diagnose it in the same way. We have a test set, right? And here is the same training plot, but now I've made up a little test set. And here's the performance on that test set as we train. So does anyone see an issue with this plot? Does anyone see a problem? Yeah, and approximately, so it's overfitting, right? Can anyone tell me what iteration it starts overfitting at approximately? Yeah, 120, right? Up to 120, it's not bad, but then it gets really ugly, right? Okay, cool. Yeah, Sai, great question. Why then? I don't know. There's some mystery in neural networks. There's no good answer for you, I don't think. There's one good answer for you. It's a great question. So here's what I really want to get into. So, overfitting is a thing. What do you do about it, right? what did we learn in the Learning to See module? What was maybe the most common or simplest way to reduce overfitting? What did we do back then? What's a very simple way we could reduce overfitting? Yeah, simpler, yeah, sure. So if we have a simpler model, right? If we have a simpler model, then it may overfit less. And that will happen, right? There's a bunch of other stuff we can do. So there's this term called regularization, which actually what it does is it kind of dumbs down your neural network to make it appear a little bit simpler. And there's a bunch of ways to do this regularization thing. We're going to talk about it a bunch. In this notebook and in the deep learning, in the neural network video series, I show something called weight decay. It's one way to regularize. You basically add this term to the end of your loss function, and it forces your weights to be small, and it makes you overfit less. So I encourage you to look at these notes on your own. This may help you on the programming challenge if you think you're overfitting, but do a test first, just see. You're going to use a very simple neural network, so you may not overfit. I'm going to skip these questions for now because I want to get into autonomous driving. I will not quiz you over these questions, so you can ignore this question and you can ignore this question. But the thing I'd like you to know is that at the very bottom of this notebook, I give you one final presentation of the neural network code. And I've introduced this extra term right here. And there's a variable called lambda. And what this lambda does is this controls how much you regularize your neural network. And regularize, it's the way I think about it is you're kind of like dumbing down your neural network to make it kind of simpler, so it overfits less. So if you're overfitting, then increase that lambda variable. So Hernan says, how does the neural network make the final decision? We presented that, Hernan, so read these notes for sure. So the final decision really is, it's right here. It's the y hat. If you're thinking about for the challenge, then that's going to be something you'll have to look into a little bit more. But here, the final decision about your score, it is the y hat. Like, that's the final decision. And I think in the video, I kind of showed the predictions that it's going to make. And I kind of show them in like 3D space, stuff like this. Here's like a set of final decisions for a network we trained, where this is your hours of sleep, this is your hours of study, this is the score. That's like the final decision of the neural network. And it's kind of predicting like a general upward trend where the more you sleep, the higher your score, which kind of makes sense. So that really is all there is to it. So please do look over this network. The regularization stuff, I would say just look over that briefly, but I won't quiz you on regularization. But you may need regularization in your programming challenge, but don't worry about it at the beginning. Try to get good results first, and then it might be something you add later. Okay, and just the last thing to know, lambda, yeah, the regularization parameter is right here, it's lambda, and you can enter different lambda values. So like when you set up the neural network, I put in a lambda of 0.001, and if I put this like lower, for example, it should overfit even less. So you have a hyperparameter that you can do. Okay, so that's really all I'm going to say about neural networks. I know that was kind of a whirlwind tour. Please do watch the videos, look at the notebooks, and you have a programming challenge that will kind of push your understanding of these things, because you're going to have to make this work for images. I've only shown it for toy data. So it's a tough one. So do get started, talk to your friends about it, talk to the TAs about it. Hardest programming challenge of the year for sure is due in a week, and it's on this topic. And the reason we're giving this to you is because I want you to have the best understanding possible of neural networks. So yeah, do start soon, and please ask us questions if anything is confusing. Okay, so we have about 20 or 30 minutes, and I want to get into our new module. We're a little bit behind, but that's okay. So let me hop into it. And like I said, if you have any additional neural network questions, ask the TAs. You can also shoot me an email, come to office hours, and we'll talk about it, because neural networks they're tricky, but at their core, they're not too bad, and I'm confident that everyone in the class can have a good grasp of how these things work. Okay. So let's transition here, and we're going to transition to our fourth module, and it's just a short little brief module. We just have 2 little lectures, really a lecture and a half, on self-driving cars. And self-driving cars they're pretty cool. I would put them kind of in one of the cooler applications of computer vision, in my opinion. I think it's a pretty neat thing you can do with cameras. And in this lecture series, we're just going to get into, what are some of the basics? What's been done in self-driving cars? We won't cover all the details by any means, but we'll kind of get you thinking about, if you want to drive a car with a camera, how do you do it, right? And there's a little neural network series that goes along with this. So I encourage you to watch that. I think it's 5 parts, something like that, but it's very easy to watch. And it will exactly mirror what we're gonna cover in lecture. Lecture is a little bit deeper, but same exact idea. Cool. So let me hop into it here. And what we're going to really do is we're going to kind of take a historical look at the history of self-driving cars and talk about the algorithms and talk about how these have evolved over time. And basically neural networks will make a nice appearance. And this will hopefully extend your understanding of neural networks as well. Okay. So here is some data. Hopefully the animation is playing okay through Zoom, hopefully. But yeah, this is some real data, and it has to do with autonomous driving. So when I give conference talks on this, I kind of like to have fun and just ask, like, what do you think we're looking at? And it's kind of fun to think about, right? And I would say that, a clue in this basically is look at the axes. They go from 0 to 250-ish, something like that. But yeah, so a couple of people say we're looking at road. That's part of it, right? Part of it. Does anyone know? Yeah, so yeah, we're looking at, make sure I get your name right. Yeah, you told me to pronounce your name, but yeah, all right, I apologize. So Akanksha, all right. Yes, road, sky, background, and trees are correct. So when we're in a meeting, tell me how to pronounce your name. I apologize. I think it's Akaksha. Oh man, Aksha. Man, it's probably really easy. All right, but your answer is really good. Road, sky, background, and trees. I apologize for name pronunciation. But yeah, well, let's get into that. But I want to actually just ask one more question. So you're right, but look at this scale for a second. This is going to be really important. For those of you not following along yet, don't worry about it. But what I'm really trying to get at here is this is a visualization of how like the first autonomous car saw the road. So this is a video of a road. But what we've done, what this first team did, so this is from a team that worked on a project called the Autonomous Land Vehicle, the ALV. This was the first autonomous vehicle back in the 1980s. So not that long ago. I was born in the 80s, so can't be that long ago, I think. So the autonomous land vehicle, what they did, they had like 9 months to build this thing. It was part of a government project. I'll talk about it a little bit more in a second. But they decided to take all their pixels and put them in red-blue color space. So hopefully this animation makes a little sense. So you take every pixel and you look at its red and its blue color value, and you can make this cool scatter plot where the x-axis is the red value and the y-axis is the blue value. Yeah, thank you. It is a cool animation, right? This one took me a little while to make, but I thought it was pretty cool. So we can put our pixels into this scatter plot, which is often called a color space. And that color space can help us solve the problem. And this is exactly how the very first team that ever made a car drive itself, this is how they solved the problem. So let's get into it in more detail. Why would they do that? What's the idea here? So this was part of the, so back in the 1980s, the world was worried about artificial intelligence. And so now I think you hear a lot of people in the US at least worrying about, I don't know if worrying is the word, but China is a rising AI superpower. There's a book on this called AI Superpowers by Kai-Fu Lee. It's very good. But anyway, the US is maybe wants to compete with China in AI. Why are my bullet points so weird? Anyway, back in the 80s, China hadn't quite modernized the way it has today, and our competitor back then was actually Japan. So Japan had this project called the Fifth Generation Project. They were spending billions of dollars on AI research. So the US said, we're not going to get beat by Japan. Let's spend some money as well. And the government funded around $1 billion into what was called the Strategic Computing Initiative. This ran from 1983 to 1993. I was born in year 4 in 1987. And this funded advances in artificial intelligence, and part of this was spending $10 million to develop what's called the ALV, the Autonomous Land Vehicle. Okay, so let's put your feet into the shoes of these engineers. So they had, they got to work on this really cool project. They said, their boss said, hey, would you like to build the world's first autonomous vehicle? And they probably said, sure. Like, that's pretty exciting. They had 9 months to deliver their first demo. At the time, their cameras were very low resolution, 480 by 512. They had very limited processing power, 10 MIPS of processing power, which is like a tiny fraction of what we have today. The vehicle weighed 15,000 pounds, which is pretty crazy. So just a crazy engineering problem. And as you know, when you take video data, right, it's just a ton of information, right? I'm showing the RGB pixel intensity values here. They had a ton of data to process quickly and not a lot of computing power. So that's part of the reason they used this color space thing like we're talking about. And I'm going to skip through this part real quick. And I want to get to this part. Here's what I really want to get to. So they had to do this. They had to figure out, how can I take this huge amount of data I'm getting from my camera and put it into my kind of small, well, it was actually a very big computer, but it had limited computational power. And how do I figure out where the road is? That was their first thing. So they actually were going off-road. So I shouldn't say off-road. It was dirt roads like this one. And they had to find the road. Okay. What I'm showing you in this visualization, I'm trying to get you to think about color. So we have our RGB image here. Here's a video that I grabbed. And what I'm showing you here in that Viridis color map is I'm showing you the red channel, the green channel, and the blue channel, right? And I'm also showing you a histogram. This histogram is a little bit special because I've colored the bars in the histogram to match the colors in the image. And you'll notice that I have this nice whitish kind of spike here. That's the sky, right? This dark greenish kind of blob, this is the vegetation, right? And this tan blob, right? This is the road. Okay, so start thinking about that. Put that in your head. And now I think I have a question for you. Yep, I do. Okay, great. So let's get a poll ready, please, guys. So what I want you to think about, my question for you, is what does the red minus the blue channel look like? What does red minus blue? So here's the original channels. Here's the red, here's the green, here's the blue. Here are their histograms. So if you just said, okay, let me take red minus blue, right? What would you get? So please take 30 seconds, look at these different answers. Which one do you think? Which one shows red minus blue? And if you say D, you're not paying attention. Okay, so B is the most popular answer, and then followed by A and C. And then one person did say D. I question, hopefully you just click on the wrong thing, because there is no D, unless you were just responding to my joke. All right, cool. So let's get into it here. And what I really want to point out, so Hernan says, hey, they look all the same, which they kind of do, but look closely here with me, right? So the green blobs are kind of the same, the white blobs are kind of the same, but look at the road blobs, right? So I know the numbers are a little bit small here. This is 150 is that number right there. So this spike is at like 170, right? This spike is at like 150, and this spike is at like 140. Why is this spike at different locations in different color channels? Why is this spike here in the red channel? What does that say about the road? That it has higher values here in general in the red channel. What does that say about the road? Any ideas? Why is this spike in the red color channel? Yeah, so Hernan is close. It's not just about being brighter, though, close. Yeah, so Videhi, I like your answer. Yeah, so Sai, yeah, you're really getting it, right? So the road, let me go back to the original image. The road is more red than it is green or blue. The road has more red in it, right? So like this is the red channel. See how this spike is further to the right? It's because they have higher intensity values. You have higher red intensity values than you have green or blue intensity values in the road. So that pattern is something that the autonomous land vehicle engineers decided they wanted to use. So if you look at the answers here, right? So when you subtract two channels, if you subtract red from blue, right? The green kind of ends up being the same. It ends up being kind of like 0. The white ends up being kind of the same because the values are so close. But the road, because you have a bigger value in the red color channel, it's like 170, and this is like 104. I know those numbers are really small, but have a look at the notebook later or the video. But because this spike is further right than this spike, you end up with a difference of around 40, and that corresponds to this answer. The answer is C. By taking the difference, by doing red minus blue, it kind of like you're ignoring the vegetation, you're ignoring the sky, but the road like pops out because the road has way more red than blue. That's the whole idea. So doing this, and notice, look at this image, right? See how the road is like the brightest thing now, right? So the road was not the brightest thing here at all. But by doing this subtraction thing, you're making it the brightest thing in your grayscale image, in your black and white image. I know this image is shown in green and purple, but remember this is just one color channel, and we're using that Viridis color map that we talked about way back in module 1. Okay, so we have a way, if we just take the red channel and subtract the blue channel, right? Maybe that will help us find the road. That's the idea here. And again, we're just following, this is exactly what the very first engineering team that built the world's first autonomous car, this is what they did. Okay, here it is in video format for fun. Right. So here it is in video format for fun. And it is like 3D glasses. Yeah, that's a good point, Adam. It's very similar, yes. So here you can see red minus green minus blue, green minus blue. And red minus blue does the best job at suppressing everything else and bringing the road out, right? So that was their idea. Okay, so who cares, whatever. So why is this useful? And my source for all of this, yeah, so Supreet has a great point. I'm gonna get to that shortly, right? What about a desert road, right? Yep, very good point. So here's the original autonomous land vehicle paper. It's very good. It's a great paper. It's written by Matthew Turk and other researchers. Matthew Turk went on to do some very important computer vision work at MIT. Here's the paper, right? And in the paper, they kind of make this look like fancy math, and it's not really fancy math, but here's the mathematical formula. So they're saying, hey, let's go compute a feature enhanced image. They call this I. And they say, hey, I is going to be a weighted average or weighted sum, excuse me, of the red, the green, and the blue channels. And you're going to weight it by using a certain R value, a certain green value, and a certain blue value. And interestingly, this is totally equivalent to doing a dot product, where you do a dot product of every pixel's RGB value with this like vector that you determine. So this is how they present this operation in the paper. And let me just ask you a couple questions really quickly. So what if we had values of 1, 1, 1 for this equation, right? So what if R was 1, G was 1, and B was 1? What would the resulting image look like? What would this kind of be close to that we've discussed before? This hopefully reminds you of something we covered back in module 1. If I just take the red, green, and blue channels and add them together, yeah, it makes a grayscale image, right? This is how you generally compute black and white images, right? So what the authors of this paper are doing is something kind of interesting. So instead of just adding these channels together, right, we talked about doing red minus blue. So the red minus blue thing, it's just using a value of R of 1, a value for G of 0, and a value of B of -1. So they're kind of, it's like a special version of grayscale, right? Where they're actually doing a difference of 2 channels. So that's the idea. And one other kind of fun thing is that if you remember back from linear algebra, a dot product, which is what we're doing here, a dot product is equivalent in linear algebra to a geometric projection. So we're projecting from a space onto a subspace or onto a line. So let me kind of show you what I mean by that. So here's one last more way to look at our data. So you can look at the data in 3-dimensional space if you want to. So here are all the pixels in 3-dimensional space, plotted by their red, green, and blue intensity value. And when you do this operation, right, what you're really doing is you're projecting these values onto a line. That's what you're really doing by doing a dot product. So what we're doing, and I have a question here, but I think I'm going to keep moving because we don't have a lot of time. I won't quiz you on this one. But when I give conference talks on this, and you can watch the video as well, I like to spend a little more time on this. But really what we're doing is we're taking this data and we're projecting it onto a line. And what that kind of looks like in practice, it looks like this. Let me get to this. So Doing the red minus blue operation in linear algebra, it's totally equivalent to taking this data and projecting it down onto this line. And the result, the data that gets projected onto this line, ends up looking like this. This is a histogram. And the reason this line works is because if you look at our three areas, right? So just like was pointed out at the beginning, these dots, this is the sky, this is the vegetation, this is the road. So if you want to maximally separate this data, then if you project it this way, this will help you separate it. It's if you had done a line that went this way, for example, right? It wouldn't have been very helpful. So the red minus blue kind of works for this reason. There's nothing magical about red minus blue, it works for this data. There's other data it might not work for, right? And we'll get into that shortly, but that's a cool way to think about what the ALV authors did. So if you look at their paper, there's one more thing they did, and it should be very familiar at this point. They do a thresholding operation where they say, okay, if this red minus blue thing, if this enhanced image, if it's less than 0, we're going to call it road, and if it's not, we're going to call it not road, basically. So this is how they found the road, and I'd like to show you how that works. So here is, 30 years later, the ALV vision algorithm. Happily, it's just in one line of Python, but all I'm doing is I'm doing that dot product. I'm thresholding, and then I'm just reshaping it basically into an image. So some pretty straightforward Python, and what I really want to show you is how this algorithm works, and I think it'll make some sense. It's not too crazy. So here's an image of a dirt road that I pulled in. There's a really good library called MoviePy that I used to pull this in from an MP4 file. This could be helpful in your project, so if you're dealing with video in Python, then check out MoviePy. So there's our image. And we're going to apply the ALV algorithm. So here we are. Here's the 1, 0, -1. This is because we're doing a red minus blue. I'm using 1, 0, -1. And I'm going to do the thresholding thing, basically. And the way it works, all I have here is just some visualization code. But the way it works is that we are going to play with this threshold. We're going to play with this threshold. And we're going to try to use it to hopefully help us find the road. Oops, I'm changing time. So I was going forward and backward in our video. I meant to do this. So if I tune this threshold a bit and just pick out the pixels that have an intensity value above this threshold, we'll start to land on the road. And all I'm doing is, I'm taking that enhanced image. Let me just go back real quick. So we computed this enhanced image by doing red minus blue. Just this, I'm just taking this image, and I'm just thresholding. I'm just saying, okay, if the value is greater than X, then I'm going to shade those pixels. And those pixels I will call the road. So back to here now. If I crank up this threshold, we should get a better and better estimate for the road, hopefully. Right? And after a little while, you see that, okay, look, wow, just by doing red minus blue and then thresholding those values, I've done a pretty good job. I mean, look at that. That's pretty cool, right? Like, there's the road, right? Awesome. I should be able to hopefully drive a car with that, right? Which is pretty crazy. So this is exactly what the engineers did. They did exactly this process. You could imagine this threshold could be a little finicky, and they would actually tune this before demos, right? Eventually, they got a lot more sophisticated, but early on, this is how it worked. This is something they would have to experiment with to find the right settings. And imagine that's driving a car, right? We'll get into that in a little bit more into detail, but this really is the whole system in action. So take your image, plot your pixels in red blue color space. We aren't literally plotting them in our out. We're just doing a dot product, but this is how I would visualize it. Take that projection, right? This represents the threshold. So the threshold, I think we were at like 25 or something. Every pixel greater than that threshold, we're going to call road. Every pixel less than that threshold, we're going to call not road. And we're going to get an image like this. And you can see it's not perfect, but it's also not bad. Like, you get enough pixels that you could probably drive. And there's some post-processing stuff they did, but this really is how the very first autonomous car, it's how it saw the world. This is how it did vision. So they had a demo, like I said, in 1985. It was just very quickly that they had to do it, just 9 months after starting. And they succeeded. So they had, the generals of the military came out to see the first autonomous, AI car. And it drove for 1,000 meters, pretty slowly. It drove at 2 miles an hour. But this was actually way faster than any autonomous robot had driven before. So remember that shaky robot I showed you back in Module 1? That thing, it basically had to sit still for 15 minutes and decide what to do. This was way faster, right? So 2 miles an hour was like a record-breaking speed. So we've got 6 minutes, and this is actually perfect timing. So we're about to get into some of the problems, right? So hopefully in that quick little crash course, that 15 minutes, I've kind of hopefully given you an idea of how the very first autonomous car saw, right? So yeah, throw these in the chat window. What could go wrong, right? You've seen how this kind of works, right? How the very first autonomous vehicle worked. When could this approach fall apart? What problems could happen? Throw it in the chat window. What do you think? So the desert, yep, snowy road, great example. Object on the road with the same color of the road, yeah, totally. Color change, rain, night, yeah, night's a thing, right? Fog, totally. Similar color, multiple lanes, yep. Grassy roads, obstacles, rain, yep. So you guys have been in the class long enough to realize that, lots of things can go wrong, right? Other vehicles, endless things, fog, yep, totally. Okay, great. So that was a great smattering of things that can go wrong. So what I did, just to kind of point this out a little bit more, I took 4 other clips. Here are 4 other clips, and I tuned the ALV algorithm to do as well as it could, and it's not doing great. So here's desert driving. Desert driving is really bad. You can see that this would try to drive up this mountain probably. Like this mountain is very much detected as a road. Here's desert driving again. Everything is road, right? Here's a trail kind of in the woods. It really struggles. Here the trees are road, so lots of things can go wrong, right? And what I'd like to remind you of is just, to me, this is a reminder of overfitting. So we only had 4 parameters in our initial model. We had the threshold, and then we had the red, green, and blue values. And there's a really great quote from John von Neumann. John von Neumann is probably one of the most important mathematicians and engineers of the 20th century. He did a lot of really important work. And he has this really great quote, which is, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. So to me, this really reminds me that with just 4 parameters, we overfit this, right? This looks great, but we overfit this tiny little video and it doesn't generalize, right? So always be on the lookout for overfitting. That's definitely what's happened here. Okay, so we talked about where it could fail. That's great. And now just to set up the next lecture, but before I do that, actually, I just want to say that, we're kind of giving these guys a hard time, but, given the technology of the day, they did something really, really remarkable. They were pretty optimistic, but this was true of autonomous driving in general and of AI in general in the 80s. This is the quote from the team, we're almost there, which, it's 30 years later and autonomous cars are kind of here, but kind of not. Depends on who you talk to. So I just think it's interesting to think about how technology progresses, but this team, given their requirements, I think just did some awesome work. And it's cool to look back and see what they did that can be reused and what's changed, what are kind of the lessons of what they did. So just a couple other fun facts. So by the end of the project, they had 30,000 lines of code running on 10 different processors in the machine. The program was basically canceled 3 years in, unfortunately. One of the criticisms the program received was that it was too demo-driven. They were always giving demos, which made it hard to actually get a lot of work done. But even though the project wasn't a complete success, it really did kick off a lot of progress in autonomous driving. And really, I think the next big thing that happened that's really exciting, which we'll talk about next time, is in 1995, which is not too much later. These 2 researchers, so Todd Yoakum and Dean Pomerleau, researchers at Carnegie Mellon, they drove this little van. They drove it across the U.S. 98% autonomously. So we've gone in just less than 10 years. We go from this ALV, which uses just really simple color-based segmentation. It goes 2 miles an hour. We went from there to a vehicle like this, right? That's the whole computer is just right there. It's much smaller. Really what starts to feel like a modern autonomous vehicle, right? So this is a huge increase in capability, right? How do we do that? So next lecture, we're really going to get into this. What did these guys, Todd Yoakum and Dean Pomerleau, they're really kind of the next pioneers in autonomous driving in the 80s and 90s. So what did they do? And you may have guessed that it has to do with neural networks, and part of the answer does. So we're going to get into neural networks a bunch next lecture. And the last point I'll make just real quick is that, the ALV, no machine learning, right? They did not use machine learning. So there may be an opportunity to use machine learning here, and you're certainly going to use machine learning on your programming challenge. And your programming challenge is kind of similar to what these researchers did, but there's some drama and some nuance to it. Machine learning does not solve all our problems, so I think that's important to keep in mind. But next time on Thursday, we're going to dive into this really deeply, and we'll discuss how did these two guys, how did they do this? How did they drive across the U.S. 98% autonomously 25 years ago? It's pretty cool, 25 years ago, cool. Okay, so that's the end of lecture. Thank you for coming today. Please start on your programming challenge and schedule a meeting with us for your group. So have a great week. We will talk to you guys on Thursday.